Hello there. In this video, we're going to keep going in Chapter 11. We're going to look at Section 11.5, which is alternating series and absolute convergence. So let's get started. So this is a special type of series called an alternating series. And the terms alternate positive and negative. So you can see that here. And it's written as just negative 1, 2, some power with an n in it. You've seen stuff like this before. So it's not like a new look for a series, it's just a new name for a series you've seen before. And we want to notice that the nth term in the series has the form an equals negative 1 to the n minus 1 times bn. So bn has to be positive. So the relationship between the an series and the bn series is that essentially the bn series is just the absolute value of the an series. So we're sort of ignoring the fact that these things could be negative. And so there's a good reason why we have to look at stuff that way, and that's really what this section is about. So when I refer to the ANs in this section, they alternate. When I refer to the BNs, they have to be positive. Now we're going to look at something called the alternating series test. This is a test for convergence. So if you're given an alternating series and that has positive BNs, and the sequence of BNs is decreasing, so that's what this means here. Right? So every subsequent term is less than the previous term, and the limit of the BNs is 0. So that means that the BNs can continue to get smaller and smaller, as small as you'd like them to get. And that's what we call the limit, right? For any finite number that you select, Bn at some point will be smaller than that and stay smaller than that number. So if those two things happen, the series is convergent. So I'm going to do a proof of this next, and then sort of later on in the presentation, I'm going to show you a graphical interpretation of this that might make it easier to understand. But first, we're going to see the proof. So we're going to look at the first two even partial sums, and we're going to see if we can develop some sort of pattern. And if that pattern holds, let's see what it teaches us. So the first partial sum is just S2, right? It's the sum of the first two terms. Well, remember, the pattern that we see is B1 minus B2, because every other term is negative. So S2 is just the difference of the first two terms. Well, that has to be positive because B2 is less than or equal to B1. Well, it has to be positive or 0, right? Can't be negative. Now we look at the second even partial sum. It's the previous sum, so it's B1 minus B2 plus B3 minus B4. So that's all we're doing is just, if we go over every two, what does the pattern look like? Right? It's B1 minus B2 plus B3 minus B4. Well, that has to be bigger than S2 because this is a positive number. And this is a positive number because B4 is less than B3. Or it could be 0. And so the general form, the general pattern is for every S2n, so we're just looking at the even partial sums, it's the previous even partial sum plus the next two terms. But because this term is smaller than this one, this is positive. And that has to be bigger than what we started with. So the idea here is the next partial sum, even partial sum, is the previous partial sum plus some positive number. And that positive number makes it bigger than the previous partial sum. So we're adding positive numbers every time we take an even partial sum. Right? And that's what that says. So our even partial sums continue to get larger. Or stay the same size, but for now, let's just think of them as getting larger. But we have another way to write an even partial sum. Because the terms in the partial sums are just B1 minus B2 plus B3, we can factor out a negative out of every other pair of terms. Right? So if I were to distribute these negatives back in, we'd get B1 minus B2, but then minus times a minus is a plus. We'd get plus B3 minus B4 plus B5. So we're just factoring out the negative. And what we're doing is we're showing that all of these terms are positive numbers, right? Because B3 is smaller than B2, so this is positive. B5 is smaller than B4, so this is positive. So here we have a number. This sum is B1 minus a bunch of positive numbers. Well, if we're subtracting a bunch of positive numbers, then this number here has to be smaller than this, right? Because this S2n is B1 minus a bunch of stuff. So the thing on the left is smaller than the thing on the right because the thing on the right has been subtracting a bunch of positive terms. Well, this is the monotonic sequence theorem, right? This is a monotonic sequence. It's getting bigger, but it's bounded by B1. And if you have a bounded increasing sequence, then it makes it convergent. So far, the proof has just been showing that the sequence of even partial sums is convergent. Because it's convergent, we can give a name to the limit, right? The sum itself, we're going to call it S, because it exists. So now we're going to look at the limit of the odd partial sums. So here we're looking at S1, S3, S5, that sort of thing. Well, this partial sum is just the previous partial sum plus the next Bn term. And this is always, again, so for example, if this is like S11 or something, it's S10 plus B11. Well, remember, the odd B's are always positive, so this is a positive number. Well, I can use limit laws on the right-hand side here and distribute the limit. We already found in the previous part of this problem that this limit is S. So I'm going to replace this with S. This limit, this is just the individual Bn terms. The alternating series test says that the limit of the individual Bn's has to go to 0, so this limit is 0. That means the limit of the odd partial sums is also S. And because we have even and odd partial sums both converging to the same value, well, every partial sum is either even or odd. So all of the partial sums, even or odd, both go to S, and that makes the series convergent to S. So that is the proof of the alternating series test. Positive B's, decreasing sequence of B's, limit of the B's, as n goes to infinity, is 0. All right, so let's see if we can use the alternating series test, and let's see what it does. So here's what we do with it. This is called an alternating harmonic series. So you recognize the harmonic series from earlier, right? It's a p series with p equals 1. And we just want to show this satisfies the conditions of the alternating series test, right? The Bn's are positive. 1 over n is positive. It's decreasing because 1 over n plus 1 is less than 1 over n, right? If you make a denominator bigger, the fraction gets smaller. And the limit of the Bn's is 0, right? Because 1 over n is a p-series with p equals 1. So the series is convergent, right? If you just plug in 1 over infinity, you get 0, right? So this converges by the alternating series test. And that's pretty much all you do for the alternating series test. You just have to show the Bn's are positive, decreasing, and the limit is 0. That's all you have to do. All right, let's do an example. So we want to determine convergent or divergent. And here we have an alternating series, so I want to use the alternating series test. But condition 2, that the limit as n goes to infinity of the bn's goes to 0, it fails for this series. So let's see why it fails. Right? Just divide by the highest power in the numerator. When I plug in infinity, I get 12/11ths, which is not 0. So this rule says it has to be 0, but it's not, right? 12/11ths is clearly not 0. So not only does this fail the alternating series test, we actually can't even use the alternating series test because we didn't satisfy the conditions. And not only did we not satisfy the conditions for the alternating series test, we actually showed that the series diverges because the divergence test says that the terms, the AN terms, have to go to 0. Well, if the BN terms don't go to 0, then you can't have plus or minus something that doesn't go to 0 and have it go to 0. So it fails the divergence test. So the reason I did this problem first is to show you that in Chapter 11, just because you're in a certain section or you're told to use a certain technique, it doesn't mean that that's the way you have to do the problem. Not every, like you don't know ahead of time what converges and diverges. So you don't know ahead of time what technique to use. But just looking at this, I can see that the terms aren't going to 0. So if I can prove they don't go to 0, then I prove that it diverges. And that's really, a problem like this is really more representative of this chapter as a whole, where you're not really told exactly what to do most of the time. You gotta just have a guess and then check that guess and see what it tells you. All right, let's keep going. Now we're going to determine whether this series is convergent or divergent. So here we have another alternating series. So just take a look at it, see if you can guess if it converges or diverges. We'll see what happens. So to show that the sequence of Bn is decreasing, we're going to use what we learned when studying the integral test. So we saw problems like this when we did the integral test. Positive Bn's, but we still need to show that every subsequent term is smaller than the previous term. We're going to learn something later called the ratio test that'll help us with this. But until we learn the ratio test, we have to use something we've already seen before. So it's hard to show directly that the sequence n over square root of n cubed plus 3 is decreasing. Instead, what we do is look at the function and show the derivative is always negative. That will make f decreasing. And if the function with x's decreases, then the function with n's in it also decreases. So that's what we did in section 11.3 when we studied the integral test. So I took the derivative of f of x, and you can see that if x is greater than 1, this is a negative number. Right? As soon as you get to 2, 2 cubed is 8, 6 minus 8 is negative, and the denominator is always positive. So any numbers I plug in here bigger than 1, so 2 or bigger, this thing's negative, which means it's decreasing. And because f is decreasing, the bn's are decreasing. So it's the functions are the same, right? One is just x's where there should be n's. All right, so we showed that the bn's are decreasing. Now we have to show, step 2, that the limit of the bn's is 0. So I'm dividing by the highest power in the numerator. Don't forget, in the denominator we have a root, so you have to put your function in terms of the root, so it goes under the radical. And now it makes sense, right? So n times 1 over n is 1. I can distribute this 1 over n squared in here. So n cubed divided by n squared is just n. And then here we have 3 over n squared, all under the radical. When I plug in infinity, this is 0. 1 over square root of infinity is 0. So we showed both parts of the alternating series test are satisfied, so the series converges. And this is pretty much what problems look like in this section. Got to have positive BNs, decreasing, and the limit of the sequence has to go to 0. Now let's talk about estimating sums. A partial sum Sn of any convergent series can be used as an approximation to the total sum, but this is not of much use unless we can estimate the accuracy of the approximation. Yeah, if we just want to estimate something, great, but we don't know how accurate it is. So the error involved in using S as an approximation for Sn is the remainder S minus Sn. The next theorem says that for series that satisfy the conditions of the alternating series test, the size of the error is smaller than Bn plus 1, which is the absolute value of the first neglected term. So that's like the maximum amount of error is the next term. So wherever you stopped, the next term can't create more error. It can only be less. So this is the alternating series test estimation theorem. So if the sum, so we're saying that S is this sum, right? Where Bn is greater than 0 is the sum of an alternating series that satisfies the two conditions for the alternating series test. Then the absolute value of the remainder is the absolute value of S minus Sn. It has to be less than Bn plus 1. So that's what we talked about in the previous slide. But here's where I said earlier in the presentation I was going to go back and talk about this. Here's where I talk about it. So why does this have to be true? Why does the remainder have to be less than the next term? So this graph pretty much tells you everything you need to know. So S is in the middle here, right? So let's say we start at 0. And then here's S1. So our partial sums, right? So we add B1, then we subtract B2, add B3. And we keep narrowing in on S. We get closer and closer to S. But why does the error have to be less than the next term? So let's just, I picked a couple here at random. So if we go from S to S4, it has to be less than B5 because as you ping pong across, you go S1, S2, S3. When I go back to S4, coming forward from S4 is B5. It has to go past S because it's an alternating series. So it's going to go past S. That means B5 is going to be bigger than S minus S4. And likewise, when I come back the other way, B6 has to be bigger than S minus S5. And so on. So because this thing ping-pongs past the difference, that the error between your current S and Sn has to be less than the next term. And that's what the theorem says. I'm not proving the theorem, but the graph should make it seem true, I guess. All right, so let's use the alternating series estimation theorem to approximate the sum of the series to 4 decimal places. So the theorem says all I have to do is find a term that's less than 4 decimal places. And then the previous partial sum will be accurate to 4 decimal places. So I just made a table. Here's my n's, here's my bn's, and here's my sn's. So I just scroll down here until I find a term that doesn't change the 4th decimal place, right? Well, that means the previous Sn has to be accurate to 4 decimal places. That's all you got to do. So 0.0768 is accurate to 4 decimal places. And as I move down the table, the next n can't introduce more error, only less. And that's how you do it. So if this looked way too easy, go back and really read that theorem, and that tells you how to use it, right? You just keep going, stop as soon as your Bn term satisfies the condition, and then the previous Sn term will be your answer. All right, now we're going to introduce another idea. So this is the last of our types of convergence that we're going to learn. We have absolute convergence and conditional convergence. So if I have a series, we consider the corresponding series the absolute value of each term, right? So why do we look at absolute values? Why does that matter? What happens? Well, it turns out that the series is called absolutely convergent if the series of absolute values, sum of the AN, is convergent. And the series AN is called conditionally convergent if it is convergent but not absolutely convergent. So there's a lot going on here. We're only introducing one new idea, but it can be a confusing idea. If the absolute value is convergent, then removing the absolute value will keep it convergent. Okay? And we saw that with the alternating series test, because what would happen is, in order for the absolute value to be convergent, it would have to pass one of the other tests. And if it passes one of the other tests, it'll pass the alternating series test. Then conditionally convergent means that if it alternates, it's convergent, but the absolute value doesn't converge. So I summarized it on this table. So we have three kinds of series now: divergent, conditionally convergent, and absolutely convergent. So there's only three things that can happen. A divergent series, doesn't matter if you take the absolute value, it's going to diverge. Conditionally convergent means if you remove the absolute value, it converges. And absolutely convergent means that it converges with or without the absolute value. And that gives us theorem 11.5.3. If a series is absolutely convergent, then it's convergent. I'm not proving it, but it should be believable based on the alternating series test, right? If it's convergent, then the sum has to go to 0. And if you alternate something that already converges, it's just going to converge faster. So you can think of absolute convergence as a stronger type of convergence. So you're going to want to memorize this. This stuff comes up all the time in future problems. So determine if the series is divergent, conditionally convergent, or absolutely convergent. Well, we see that it's alternating, so maybe we want to use the alternating series test. So the BNs are positive, right? Got to show that. So I'm going to do what I did before. I'm going to replace x or n with x. I'm going to show the derivative is negative, so that shows it's decreasing. Right? So there you can see that this derivative is always negative, right? So because the derivative of the function is negative, the function itself is decreasing, and therefore the sequence of the BNs is decreasing. Now, the second part of the alternating series test says that we have to show that the sequence of BNs goes to 0. Well, we can see that it does, right? It's just 1 over n to the 5/6. Each term, as I plug in infinity, goes to 0, right? 1 over infinity is 0. So the alternating series test tells us that this converges. So when you're doing the homework or a test, they might converge, they might diverge. You just have to look at the problem, see if it looks like something you've seen before, and start messing around with it, really. Now we're going to look at the absolute value, because just because it converges, that doesn't mean that it's conditionally convergent. It could be absolutely convergent, so we check the absolute value. So the absolute value just gets rid of everything with a negative, and I rewrote this as n to the 5/6. This diverges because it's a p series. And so if it's conditionally convergent, which is what this is, then the ANs converge, but the absolute value of the ANs diverge. So this is conditionally convergent. So this is how you want to write it when you're doing the problems too. So if this is a test question, this is pretty much what you want to show. Again, use the table a couple slides ago. It really helps with trying to figure out divergent, conditionally convergent, or absolutely convergent. All right, almost done. Last thing we want to talk about is called rearrangements. You don't have any online homework for this. I did put a problem at the end that you can do for bonus points. If we rearrange the order of the terms in a finite sum, then of course the value of the sum remains unchanged. But it's not always the case for an infinite series. By a rearrangement of an infinite series, we mean a series obtained by simply changing the order of the terms. For instance, a rearrangement of the series sum of the AN could start as, so I just made this up, A1 plus A3 plus A7 plus A2 plus A20 plus A19. You can put these in any order you want. And it turns out that if your series is in fact conditionally convergent, this is what happens. So if your sum is absolutely convergent, then any rearrangement of the sum has the same sum. However, any conditionally convergent series can be arranged into a different sum. In fact, if the sum of the AN is a conditionally convergent series and R is any real number whatsoever, then there is a rearrangement of sum of the AN that is a sum equal to R. So what this basically means is, for a conditionally convergent series, the terms can be rearranged to equal any number. So there is, again, there is a problem here at the back that you prove it. Go ahead and give it a shot. Take a picture, upload it. I'll give you 5 bonus points on your test. All right, well, that's it for this video. If you got any questions, let me know, and I'll see you guys next time. Bye-bye.